Hello everybody. We're gonna solve one example on the unsteady state molecular diffusion in semi-infinite mediums. And this example is about silicon wafer and doping the silicon wafer with phosphorus. So this is a process that is done to change the properties of silicon wafer related to the semiconducting properties and these kind of things. So what's important for us here regarding the mass transfer part is that there is a reaction that takes place between the phosphorus oxychloride, which is this compound, and this reaction takes place between phosphorus oxychloride and silicon. This is the reaction that takes place here. It produces silicon oxide and chlorine gas and phosphorus solid. So the layer of silicon oxide is rich in phosphorus. So there is a lot of atomic phosphorus in this layer, which acts as a source of phosphorus that diffuses through the silicon layer. So this is the silicon layer, which is this, and phosphorus diffuses through this. There are a lot of information here that might not be very important regarding the mass transfer part here, but this paragraph here is the important one, and that's why I'm gonna read it to tell what's important here. So it says that we consider the simplified case where the silicon wafer initially had no phosphorus. So in the very beginning, before the reaction starts, the concentration everywhere of the silicon wafer is 0, or phosphorus in silicon is 0. And after the beginning of the reaction, the phosphorus atoms concentration is constant at the interface. So at this interface here, the concentration of phosphorus is constant. And the diffusion coefficient of phosphorus in crystalline silicon is very low, and only a thin film of silicon phosphorus is desired. So the concentration the diffusion coefficient, so the speed of diffusion is very, very slow. And phosphorus atoms do not penetrate very far into the silicon, and this is the important part that we can deduce from it the semi-infinite condition here. So the phosphorus atoms cannot see through the entire thickness of the wafer, and the silicon solid serves as semi-infinite sink. So this is what the statement of the problem says, that the phosphorus diffuses very, very slowly, and it's not gonna go all the way to the other end of the silicon wafer. So this tells us clearly that this is a semi-infinite medium. And of course we can tell from here that there is time dependence, because in the beginning there were no phosphorus, and then the concentration increases as time increases. So this is a time dependent process, or an unsteady state process. So now the information that we know, that the concentration of phosphorus at the interface or at the surface is 2.5 multiplied by 10 power 20 atoms per centimeter cube of solid silicon, which can be divided by Avogadro's number and give us the number of moles if you want, but I'm gonna keep it like this. And it's very diluted. The diffusivity of phosphorus in silicon is this 6.5 times 10 power minus 13, which is a very, very small number. And the phosphorus rich coating is considered as an infinite source relative to the amount of phosphorus amount transferred. So this is the source, and CAS is constant. It's required to predict the depth of silicon phosphorus thin film after 1 hour, and at this thickness, the target concentration is 1% of the surface value. It's 2.5 times 10 power 18 atoms of phosphorus per centimeter cubed of silicon, solid silicon, and to get the concentration profile. So let's first state the assumptions that we have. So it's an unsteady state process. We know that it's a semi-infinite medium. It's one dimension diffusion in z direction. We have constant boundary conditions and constant temperature, pressure, and constant diffusivity. So this, and of course there is no reaction in the diffusion during diffusion. So these are the assumptions that we have. So now we can state the initial boundary conditions and the equation that we are using. So the initial condition is that at the beginning there is no phosphorus at any part of the silicon wafer. So at T equals 0, C equals 0. And the boundary conditions is the C at z equals 0, C is CAS, which is 2.5 times 10 to the power 20 atoms phosphorus per centimeter cube of solid, and at z equals infinity, C equals 0. And we could tell that z equals infinity because of the semi-infinite assumptions that we made. And based on the given assumptions that we have, the continuity equation reduces to this shape. Having this differential equation with these boundary conditions and initial conditions, it's the same case as before. We have two equal constant conditions, one initial condition and the boundary condition at z equals infinity, and we have another constant value of the boundary condition at z equals 0. So the analytical solution will take the same shape that we did before, so we don't have to go through the same derivation one more time because we have already done this, and this is the shape of the results of the differential equation. We know Ca, which is 1% of CAS, and we know CAS, we know Ca node, so from this we can get the left hand side of this equation, which is 0.99. And then this means that the error function of this function is 0.99. And if we recall the error function graph that we showed before, this error function here, it's very difficult to get the value of 0.99 because it's gonna be hard from here. So the graph is not usually used in these cases because we don't get accurate values from the graph, so it's better to use the table. So in this table we have values that are in the graph you can tell that it's somewhere between 1.5 and 2, but you cannot tell exactly. At 1.5 it's 0.96, and at 2 it's 0.995, so yeah, it's somewhere in between. You would see that it's 0.97, 0.98, 0.98, and then 0.992. So this is somewhere between these two values, between 1.8 and 1.9. And by doing the interpolation, you can give or get the value of 1.82. So now we can just substitute in the equation. I know I want to get z, and I know diffusion coefficient. I know time is 1 hour, which is 3600 seconds, and from these I can substitute and get the value of z is 1.76 times 10 power minus 4 centimeter, which is 1.76 microns. The concentration profile will look like this if I plot the at time equals 2 hours, 1 hour, I'm sorry, and get the concentration as a function of z. Then this is gonna be the concentration profile, and this is how it looks like. But there is a question that might jump into your minds, and this is like a very valid question. This is the profile of a concentration based on the equation that we used before, which is this equation, the error function equation, and it's looking like this. However, before, when we did the derivation and we plot the concentration profile, the profile that we got was different. It took this shape. So we should expect that the profile that we get for the current problem to be the same, to go down and then plateau at the end. But actually, the two graphs are the same, but this is plot on a log scale. You would see, because we are using the concentration as number of atoms, the number is big. It's 10 power 20 something, and that's why we have the range starting at 10 power 24 and ending at 10 power 19. So we have almost 5 orders of magnitude difference between the maximum and minimum points. So if we plot them on a linear scale, then you have to expand the scale a lot so that you can get the value of, or the maximum value, and then the minimum values will be lost. And this is what we see here. This is the same data set. We have it plot here on a log scale, and you can easily see each point on the log scale, but on the linear scale you would see you have the maximum point 2.6 times 10 power 20. It should be 24. I think this is 24. This is, I think, a mistake. But the values here starting the depth of 1.6 almost, they all look the same, or from 2. So I'm missing all these data points because I cannot see them on the graph here. So it looks like this, which is the same shape, but to be able to get to see the actual values and to distinguish between these points, which all look the same here, we can use the log scale to make the values clear. So usually we use log scale for data with very big difference in the powers, and this is what makes the log scale useful in these kind of cases. So this is the last thing in the problem. In the next video, we'll start talking about the molecular diffusion in a finite medium. And this is going to be the last thing that we cover in this chapter. I'll see you in the next video. Goodbye.